Hello everyone. Have you ever wondered what your perfect study environment might be? Well, I guess we have created something that might help you out with that. Hi, my name is Ibrahim Faris, and we've developed a machine learning project specifically for university students. And our goal is to predict your ideal study environment based on your preferences and habits, making your academic experience probably more productive and enjoyable. And in this video, we will walk through the code of our project and the steps we've taken to build our project. So stay tuned as we dive into the details of our project. So firstly, here we imported the necessary libraries for our project, and we imported the dataset we used. We collected this dataset ourselves using a Google form, as you see right here, and here's the head of that dataset, and this dataset consists of 155 entries or rows and 8 columns, which the first column is the target column, where you prefer to study the most. And for data preprocessing, we started by changing the names of those columns. As you see here, the names of the columns are questions, so it's kind of hard to deal with. We just changed it to some more simple names like study environment, motivation, noise level, etc. And we found if there's any NaN values or not a number, and null values or missing values, and all of them are zeros, so there is no any missing values in our data set. And here we have some columns with categorical features: motivation, environment with others, alone or with others, and study time. So we decided to use one-hot encoder with those features, since they're not ordinal, so we can't use label encoder, so we went with one-hot encoder. And for Y, or its study environment, we used label encoder. And we have 4 labels: cafe, home, library, and park. And here is just a brief description of X, the count of each one, the mean, the standard deviation, minimum and maximum. And here are the unique values of each of the columns. And here we calculated the variances of those features. And here is the target distribution of our Y value. We see the home is the most available value, and the dataset is highly unbalanced, so we need to deal with that before training our models. And here is the correlation matrix of the independent variables. As we see here, the features which we used one-hot encoder with are kind of highly correlated, so we also need to deal with that with feature selection before training our models. And here's some data analysis of our independent variables, so distribution of each one of them, of the noise level, lightning resources, and some other features. And here are the box plots of the 4 features with 5 different values, which are noise level, lightning resources, and comfort. We see in most of them the most responses were between 3 and 5, so that tells us something. And here I applied upsampling on the dataset to balance the values of Y. And here I used forward selection with random forests for feature selection, and the results are those are the features that were selected with the best accuracy, and the number of them were 15. So we went from, I guess, 17 or 18 to 15 features. And here we just split for train and test data using 20% to 80% ratio with the random state equal 42. So now for the models, firstly we just declared some dictionaries to store the results of those models to compare them later. And our first model was the random forest, so we started by training it using the default parameters, and we trained it on the X-trend resampled and Y-trend resampled, and we got an accuracy of 0.827. And then I used grid search for hyperparameters tuning, and this is the grid we used. And after running this code, it took around 20 minutes. We got the best parameters to be bootstrap false and max depth to 90, and I just put those parameters here to use the same model again without needing to just do the grid search. And the accuracy were actually the same, which is 0.827, but surely the precision, recall, F1 were changed, and we will look into those later. And after applying k-fold cross-validation, we got the score of 0.858. And our second model was gradient boosting. And as before, we started with the default parameters. We trained it on the X-train resampled and Y-train resampled. And we got an accuracy of 0.813, which is less than random forests. And after using grid search with this grid, we got those as the best parameters, and also I just put them here to not do the grid search again. This grid search took about 15 minutes, which is less than random forests. And we got this accuracy, 0.827, which is the same as random forests. And after applying k-fold cross-validation, we got this accuracy. And our third model, we decided to go with neural networks. So firstly, I defined a function that creates a model taking 3 parameters: layers, number of hidden layers, start number, the number of neurons in the first layer, and the dropout rate. And I started, it will be a sequential model with all the layers will be dense, so it's fully connected model, and the activation function for all the layers will be ReLU, but in the output layer it will be softmax. And here I'm just building the hidden layers, and in each layer I'm dividing the number of neurons by 2. And for the last layer, the number of neurons will be just the length of the Y, which is 4 here. And here I compiled the model using Adam Optimizer cross entropy loss function, and just returned the model. So this function will help a lot later when I did the hyperparameters tuning. So I just started with some random parameters, where 2 hidden layers, starting with 128 neurons and 0.2 drop rate, and I trained the model with 75 epochs and 32 as the batch size. And after this training, we found the accuracy to be 0.83. So this accuracy is better than any model we trained before. And after that, I defined a grid for training the model with different number of hidden layers, start number, dropout, and epochs. And here I just used brute force to train models of those parameters. So this training took around an hour and a half, I guess, or hour and 20 minutes. So it took a long time. And after training, we found the best parameters to be those 4 hidden layers, starting with 256 neurons, 0.1 dropout rate, and 100 epochs. And I just put those parameters here and train the model. And here I just save the model so I can use it later without the need to train it again. And we got the accuracy of 0.89, which is a good accuracy. And now for the last model, I decided to go with stacking, just to make it more interesting. So firstly, I defined a class to make our life easier. It's called stacking model, which is inherited from logistic regression. So logistic regression is going to be our meta classifier in this stacking model. So we gave the constructor models parameters. We give it the models we're going to use in the stacking, and this method for preparing the data to use it in the stacking. And here just redefine the fit, predict, and predict probability for logistic regression to prepare the data, then do the fitting, prepare the data, do the prediction, and etc. And here I started by defining the model using the models we trained before: ANN, neural networks, GBM, gradient boosting, and random forests. And I trained the model here, and here I calculated the accuracy to be 0.88. And here we calculated the AUC score of each model. and those are the classification reports of each model before and after the hyperparameter tuning. And now I'll leave with my friend Mulham to explain to you the analysis of those reports.
And now we will examine their accuracy, F1 score and AUC scores both before and after tuning to access their performance and improvements. The first one is random forest classifier before tuning accuracy of 0.83%. With a balanced micro F1 scores of 0.84, and after tuning accuracy remained 0.83 with slight gains in home and library precision. AUC score 0.954 indicating strong performance. The second one, gradient boosting machine. Before tuning accuracy of 0.81 with moderate performance for library. F1 score is 0.70. After tuning accuracy improved to 0.83 with gains in library and home recall. AUC score is 0.956, showing excellent discrimination. And the third one is artificial neural network before tuning accuracy of 0.83 with moderate performance for home. F1 score is 0.69. After tuning accuracy increased to 0.89 with significant gains in home and library F1 scores. The last one is the stacking model. The accuracy reached 0.88 with a strong performance for all classes. Micro F1 score is also 0.88. AUC score 0.959, indicating strong reliability. So, and here we put them in tables to be more organized, and here is the tables before and after. So, and thank you, and now we are going back to my friend Ibrahim. Thank you.
Thank you, Mulham, for explaining the classification reports. And here we have a simple graph of the accuracies before and after we did the hyperparameters tuning. So for random forest, we see the accuracy did not change. For the gradient boosting machine, we see a slight increase in accuracy. With neural networks, we see a high increase, so it was 83% to 89%, which is good. And for stacking, we did not do hyperparameters tuning, so just one accuracy. And here we have confusion matrices for our models, starting with random forests, gradient boosting machine, stacking, and neural networks. And here we did unsupervised learning using hierarchical clustering. We chose our linkage method to be the complete linkage, and here we just plotted our dendrogram, and we chose the number of clusters to be 4 by following the longest vertical line. We made the cut here, so we got 4 clusters, and here we just defined our clusters to be 4 and did the clustering here. And we see the number of points for each cluster, and here we used PCA to map our clusters to 2 dimensions, so we can plot them using scatter plot. And here is our scatter plot. We see we have 4 clusters. The first cluster, the blue one, is isolated to the low left, and the other 3 have some overlapping, so it could be some ambiguity between those clusters. And here we reach the end of our code for the model. And now for the next part, we have the UI. We developed a simple UI for our code, and this is the UI. We developed it using HTML, CSS, JavaScript, and we made the backend API using Python's Flask. And I'll just take you over the code. So this is the code for the backend. So we used Flask. We imported our ANN model, which we saved earlier, and here it's simply taking the inputs from this endpoint, which is /predict, and using this model to make the predictions and returns it as a JSON file. And here for the JavaScript file, it just took the values from the form the user submitted and make an API call to the backend, and will print the results on the screen. And here let's try it. So I'll start with noise level, not important, lighting not important, resources not important, comfort not important. I'll go with minimal distractions as my motivation. When people are around, I'm distracted. I prefer to study alone, and I usually study in the morning. Let's predict here. We see the best environment is the library, those are the probabilities with our prediction. So let's try to change some of those to random inputs, and here we see it's changed to cafe. Let's change a little bit. Here it's still cafe, but the probabilities change a little bit. So it's just a simple UI that the users could use to predict their own preferred environment. And now I'll keep you with my friend Helmi, that will talk about some research papers and articles that helped us with building our project.
Hello. In our articles, we used random forests for Bremen in 2001, journal Machine Learning. Key findings of it: introduced the random forest algorithm, enhancing its accuracy and robustness in classification tasks. Relevance to the project: validate the use of random forest as a reliable algorithm for classification and noise handling. And we used gradient boosting for Feud and Spire in 2016. A journal of it is ACM CKDD. Key findings of it: presented the gradient boosting framework, highlighting its ability to optimize productive performance iteratively. Relevance to our project: supposed to inclusion of gradient boosting as a powerful method for enhancing predictive accuracy. Third article: artificial neural networks for Lemmerhalt and Hinton, 1986, Journal of Nature. Defined fundamental concepts of artificial neural networks and backpropagation for deep learning tasks. Relevance to our project: guided the use of ANNs for complex pattern recognition and deep learning experiments. Fourth article title of it: stacking for Wolpert in 1992, journal Neural Networks. Key findings of it: proposed stacking as a method for combining medications for multiple models to improve overall accuracy. Relevance of our project: motivated to use of model ensembling techniques such as stacking to achieve higher predictive performance. Last article: hierarchical clustering for Sneath and Sokal in 1973, journal Numerical Taxonomy. Introduced hierarchical clustering as a method for grouping similar data points into nested clusters. Relevance to project: provided insights into the use of clustering techniques for unsupervised learning and data organization. This is all of articles, and the reference for project is here if you want to the links for it. This and Dremel Heart here, this one. And my name is Hilmi. Thank you.
So that's a wrap on our exploration of how we built our project and how machine learning could help you to understand your preferred studying environment. So thank you for watching, and if you have any question or thoughts, feel free to leave them in the comments. See you next time.